Okay, so let's get started. This is about 6.3 central limit theorem. Here we are going to look at the distribution of sample means. So what does mean by sample means? Look at these example. Suppose if you are given a population, say you have say 100 data values here. Say you have 100 of them. Now, I'm telling you, hey, could you choose say 50 as a sample size, for your sample and find the mean of your sample. Okay. So what does mean by that? That means you are asked to draw 15 of data values among here. So you are choosing. So you are asked to choose 15, right? 15 of these 100 values. Okay. Then you are putting that into your sample. So here, if you look at, you will have, x1, x2. So you choose here. Here you are choosing, say, 15 of the data values. You are choosing randomly 15 values out of 100 and putting into your sample, right? So here you will have 15 data values from here you are choosing, right? So let me call those 15 data values, say y1, y2, say up to y15. So here your sample size is 15. Here the population, say population size is 100. So now you have sample and we know how to find the sample mean. So you will find the sample mean, say that I say y bar. So this is my sample mean for this particular sample, right? Remember, there are so many ways to choose, the 15 data values among 100, right? How many ways you could pick these samples? So you could pick in, 100, choose 15 ways, right? This much number of ways you could choose your sample. So that means you will have plenty of, possible samples. So you are choosing among those, choices, you are choosing only ones, right? There are plenty of many other sample possible values are there. For each, the possible values among these 100, choose 15, you could find like this by bar, right? That by bar now will change, right? That depends on your sample, right? So that means if you put all y bar, possible y bars, possible sample means, then those kind of, the possible values are called the sampling distribution. So you are thinking about the samples, samples of these kind of, the sample sizes. So that is called the sampling distribution, right, of the sample mean. So you are looking about, the distribution of the mean. So if you look at that distribution of the mean from your sample, that is called the sampling distributions of sample mean. Okay. So now here we are going to look at this kind of, the values, the mean of your samples. Okay. So we are going to look at the properties of, the mean of your samples. Okay. So now if you look at the second definition, so this is about the sampling error. The sampling error is the difference between the sample measure and the population measures, right? So remember, we are estimating your the parameter value of population by looking at your sample. So when you estimate something, we will have always, the difference, that difference between the original and the your estimated. Those differences are called, the sampling errors occurring when you estimate something, right? So that is about this definition. The properties of distribution of sample means. So what kind of properties we have for the distribution of a sample mean? The mean of the sample mean will be the same as the mean of the population mean. What does mean by that? Suppose population variable I am taking as x. This x has now different values. So I have here n of them, big N of them. So x is a random variable here. So the mean of x is now, if you assume mu, and the standard deviation of x is say sigma, then if the sample size is little n, that means you are drawing little n of the data values from this population, and you are finding mean, and you are collecting all the possible means. Okay, so that is I am rewriting those two variables. The variables are as x bar. So x bar is nothing but my sample mean. Okay, so here according to my picture, I have y1 bar is one of those, y2 is another, and so on. So you have plenty of mean values. Okay, that variable, the values are denoted by x bar. So x bar is here variable. Okay, so what kind of variable? This is nothing but the means of your sample. Okay, suppose if you know the mean of the population, that mean of x is say mu, and the standard deviation of x say sigma, then mean of x bar is we denote by then mean of x bar we denote by mu of x bar, mu sub x bar you could read. That is always equals to your population mean. And the standard deviation of your x bar, so we denote that by sigma subs of x bar, that is always equals to the population standard deviation sigma. Then you need to divide by the square root of your sample size, little n in my case. So this is kind of properties, two properties we have. That is the one here they have explained. The mean of the sample means will be always the same as the mean of the population mean. That means what? That means, in summary, mu of x bar is always going to be equals to mu. And standard deviation of x bar is always going to be the sigma over square root n. Okay? So the second one, the standard deviation of the sample means, that means they are talking about sigma x bar, will be always smaller than the standard deviation of the population, and it will be equals to the population standard deviation divided by the square root of the sample size. So we are going to use these two, the mean and the standard deviation for what? For the sample mean. Okay, remember here x bar also a variable, right? X bar may have so many values, right? Different mean values of your sample. Okay, now these are the two properties, and the third property of your sampling distribution will follow this theorem, which is called the central limit theorem. When you increase your sample size, little n, the shape of the distribution of the sample mean, right, taken with the replacement from the population with mean mu and the standard deviation sigma will approach the normal distribution. What does it mean by that? That means, suppose if you have large number of samples, right, sample size, and if the mean and the standard deviation of the population, then the distribution of your the sample mean is always going to be approximately to the normal, regardless of your distribution of your original x. Your x may be normal or may not be normal, but if you have the large number of sample size, then your sampling distribution may always going to have, with the normal approximation. Okay, so this is very, very useful theorem, and the mean of your that distribution of mean is going to be mu and the population mean, and the standard deviation is here I need to write down. which is sigma over square root n. Okay. So now this is the note you need to include. So make sure that you include this in your note. This is not there in your note. Make sure that you are including these couple of notes. So it is important to remember two things when you use the central limit theorem. When the original variable, that means they talk about the x, when the original variable is normally distributed, then the distribution of the sample means, that means the distribution of x bar will be always normal distributed. If the original one is normal, then x bar also going to be normal, right? So for any kind of sample size little n. But when the distribution of the original variable x is not normal and the sample size is 30 or more, right? Then by the distribution of x bar is always going to be approximately the normal. So when you have a large number of sample sizes, then the distribution of x bar is always going to be normal, whether x, the original variable, has normal distributed or not. Okay, so these are the two important properties we have under sampling distributions. So when you do some problems, then we will understand about the distribution of x bar means, okay, sample means. Okay, so look at this problem. The average drive to work is 9.6 miles. Assume that the standard deviation is 1.8 miles. If a random sample of 36 employed people who drive to work are selected, find the probability that the mean of the sample miles driven to work is between 9 to 10. Okay, so what is the question actually? The question part is here. This is the question part, right? So you need to find the probability of what? Of the sample mean. They are asking us to find the probability of sample means x bar that will be between 9 to 10 miles. This is the one they are asking us to find out. Okay, so what is x bar here? X bar is the variable that is mean of your sample miles. So that is the meaning of x bar. And what is my x here? X is the original variable they are talking about at the beginning of the problem. The average drive to work is in miles, right? This is distance. So the distance for the work, that's my original variable x. Once you have the distance as your original variable, then x bar is nothing but the mean of the distance, right, from your sample. That is why it is called the sample miles. Okay. So if you look at the problem carefully, so the given information pieces are the mean of what? Mean of original variable x, the distance. That is given 9.6. And the standard deviation, so we use, this is nothing but in mu, right? The standard deviation of the variable x, that is given, standard deviation is 1.8, so which is 1.8, so that is sigma. So these two are given information pieces for the original variables. Okay, so now I could use the central limit theorem since my sample size is now 36, right, which is bigger than 30. So you could consider this number as a large number, large sample. So that means what? That means by central limit theorem, the distribution of x bar is normal with mu of x bar. The distribution of x bar is normal with the mu of that distribution x bar is always going to be equals to mu That is, we know for the original data, we know mu is 9.6, and the standard deviation for x bar according to my formula, which is sigma over square root n, right? So if you go back and check the condition I have given here, that means the standard deviation of x bar is standard deviation of original divided by square root n. Okay, so the original standard deviation, we know that is a 1.8, that is a 1.8 over divided by square root of n is 36. So if you simplify this one, so which is zero point 0.3. Okay, that means what we got now are two numbers. So we got two numbers. So we got two numbers, right? Mu x bar and sigma x bar, the mean and the standard deviation of x bar. Okay, so we know now two numbers. Okay, now let us do the problem. Now you know the distribution of x bar, right? Normal with mean 9.6 and the standard deviation is 0.3. What was the question? Question is now finding, the probability of x bar between 9 to 10. Okay, since x bar is normal distributed, so you could use now normal distribution curve, right? So if you draw the picture for this problem now this is my normal distributed curve. But remember, my variable is now x bar. They are talking about x bar. Okay. Then what is the mean of a central point of my x bar? That is my mu x bar. Okay. That is given. We know now. We found that. That is 9.6. But you need to find the probability between 9 to 10. So 9.6 is here. 9.6 is here. So 9 will be somewhere here. And the 10 will be somewhere here. We need to find the area of in between region. This is the area we need now. Since my curve is normal distributed curve, so you could use the normal CDF function to find the area. Okay, remember x bar is now normal distributed variable, not standard. Therefore, when you use the calculator, you need to define the parameter for normal CDF, since this is not standard normal. Okay, my left bound is 9 for the area colored, and the upper bound is 10. Now you need to put what? You need to put mu x bar and standard deviation of x bar, because I'm talking about the distribution of x bar, right? Okay, make sure that you understand that point. Okay, now simply plugging those values. So normal CDF and 9, 10. What is mu x? What is mu x bar? Mu x bar we got 9.6. And my mu x standard x bar, right? That means standard deviation of x bar is 0.3. Now when you type this, you will get the answer. So let us type those values here. So I'm going to normal CDF and 9, 10 and 9.6, 0.3, and you find the probability, that is the area. So my 2 decimal place answer is 0.89. That is the the probability of being your sample mean between 9 to 10. Okay, so this is one way of doing this problem. But if you want, now remember, the second method, you could change this one into standard normal and do, right? The second method is what? Use the standard normal formula. The standard normal z is given by X bar, now I am talking about, you have to subtract the mu of X bar over standard deviation of X bar, right? So recall the last section we learned, you know, the standard normal formula always given by X minus mu over sigma. That is for the distribution of X. Now instead of X distribution, we have X bar. Therefore, you need to replace X by X bar and mu by mu of X bar, and this standard deviation as sigma of X bar. But this will be given mu of X bar is equals to mu, always the population mean, over sigma X bar is always sigma over square root n. Therefore, the new formula we have now, what? The relationship between standard normal and the mean, sample mean. So make use of this formula if you want to change, the given X bar values into standard normal. Okay. So if you want to do this problem, the original question was X bar finding 9 to 10. Okay. So let me draw the picture one more time. Suppose if we keep these two values as say x1 bar and x2 bar, so now you could change this picture into the standard normal. So use the standard normal formula. So use z as x bar minus mu over square root standard deviation over square root. If you use this formula, so I'm going to change x1 bar to my z1. Okay. So what is that? So I'm finding z1 for when x1 bar is 9. Okay, 9 is here. This is my x1 bar. So when you plug in that value into your formula, so you will get z1 as 9 minus mu for this problem is, remember, mu is 9.6, and the standard deviation for the original problem was 1.8. So I'm plugging those two values, 1.8 over square root 36. So if you simplify this, this should be 9 minus 9.6 is 0.6 over 0.3, right? So that is going to be simply 2, but this will be negative, right? Negative. That is a negative 2. Now take the second point, x2 bar as 10. Then find the second corresponding standard variable z2, standard value. So that is 10 minus, and again I'm using the same formula. 10 minus mu is 9.6 over 1.8 over square root 36. So this will give you 10 minus 9.6 is 0.4 over 0.3. So that is 1.33, right? That is my Z2. Basically, I am converting my X bar into, the standard normal Z. Now, if you draw the new picture for the standard normal, the center point is now 0 for the standard normal always. My X1 will be Z1 now, but that is a negative 2. And my x2 bar is going to be, my x1 bar 9 is now going to be negative 2 in standard normal picture, and x2 bar 10 is going to be now 1.33 in my standard normal. So now we need to find this area. Remember, now we are very good because picture is for a standard normal, therefore the area I wanted is simply normal CDF for negative 2 to 1.33, right? Find that answer. So that is again 0.892 decimal places. You see, now we got the same answer as the earlier method. So you could choose either way, but I prefer first method, right? Because you don't need to do a lot of work here. So simply do the problem as it is in terms of X bar without changing into a standard normal. Okay. Okay, so let us move to the second example. The average time spent by construction workers who work on weekends is 7.93 hours. Assume the distribution is approximately normal. So that means here the variable is the original variable x is they're talking about what? They're talking about, the time spent, right? The time spent. So it's going to be our original variable x. So if you read the question carefully, the average time spent by the construction, that means the mu average for this original variable x is given, which is 7.93, and assume that the distribution is normal and has the standard deviation is zero point 0.8. Therefore, the standard deviation is 0.8. So these are all about, the information pieces for original variable x. Let's look at the question then. The first part is to find the probability that an individual who works at that trade works fewer than, 8 hours on the weekend. Therefore, the first part is nothing but we need to find out the probability of the original variable x, which is less than 8. Okay, that is the one we are looking for the first part. For the second part, if a sample of 40 construction vehicles is randomly selected, find the probability that the mean of the sample, therefore here they are talking about what? X bar. That should be less than 8. So now this is my second, problem. So the first one is they are asking about the probability of, for the original variable x less than 8. For the second part, they are asking about find the probability of the sampling distribution mean x bar, which is less than 8. Okay. So first of all, we need to understand the question carefully. Okay, so let us find the solutions for both of them. So the first one, remember the distribution of x, the distribution of the original variable x is they say that is normal. Therefore, I could draw the normal curve. Okay, this is about my original distribution x. And if you look at the midpoint, mean of the original variable x is mu, which is 7.93. Okay, and the standard deviation for this problem is zero point 0.8. Question is what? Question is now first part, finding the probability of x which is less than 8. Remember the probability means nothing but the area under the curve. So 8 will be somewhere here. Therefore, we need to find the, the probability of being less than 8. Less than means the left side of 8. So you need to find this area. Okay. Remember, we know now x is normally distributed. Therefore, you could use the area formula normal CDF in your calculator to find the probability. So this is nothing but the normal CDF. So you need to put the bounds for the area. Remember my left side, the bound, left bound is negative infinity. Therefore, it is negative E 99. The right bound for the area is 8. Remember, x is normal, not standard normal. Therefore, you need to define mu and the standard deviation in your function. Therefore, if you put those values, you will get a normal CDF with negative E 99, 8, and mu for the problem is 7.93, and the standard deviation was 0.8. Okay, then type this all into your calculator and find the value. So you should get a 0.53 as the 2 decimal places. That is the probability of being the original variable, the working hours, which is less than 8. Okay. But if you move to the second part, now you need to think about the sampling distribution, right? Because we need to find out now what the probability of x bar being less than 8. Okay. So remember, my sample size is 40 now. They're talking about, the 40 sample workers is now normal. because of center limit theorem. Therefore, if you look at the distribution of x bar now, the mean of x bar, which is always going to be equals to the original mu that is given in the problem 7.93, and the standard deviation of x bar, that is formula says that the original standard deviation divided by the square root of sample size. The original standard deviation for the problem is 0.8, and I'm dividing by the sample size, which is 40, so square root 40. So this is approximately to decimal point will be 0.13. Okay, so I need now this information, pieces for finding the area for x bar. So now if you draw the picture for x bar, remember now x bar is normal distributed. Therefore, I'm free to draw a normally distributed curve. I'm talking about now x bar. So the center point, the mean of the x bar, which is mu x bar, we know that is equals to mu 7.93. But now we are looking for the area less than 8, so 8 will be somewhere here. Again, you need to find the area, left side area to that 0.8. Okay, therefore the probability of x bar less than 8 is, again I'm going to use the normal CDF function in calculator, and the bounds again negative E99, and the right side bound is 8. But remember now I need to define my parameter mu x bar and the sigma x bar, because I'm going to find for x bar distribution, right? So this is the normal CDF, negative E99, 8. So my mu x bar was 7.93, my standard deviation x bar, sigma x bar was 0.13. That is 0.13. When you find this answer, it should be 0.7. Okay. So this is the probability of sample mean x bar being less than 8. So two different distributions so we used to here. Okay. Then you can go through the exercise problem and let me know if there is anything difficulties. Okay.